So in the last class, we learned about representing the wave function in the position space. So wave function in the position space. In the position space. And we learned that if you apply the operator x on a ket eigen function, x prime we did, so let us take x prime. So it will be the eigenvalue x prime times the eigenvector x prime. So, so effectively the operator operating on eigenfunction gives the eigenvalue times eigenfunction. So that's how what you learned earlier. And the orthogonality condition was that x, let us say x double dot x dashed, this will be delta x double dashed minus x dashed. Okay, and this will not be so. So if you take the same thing, x dashed here, x dashed will not be equal to 1. It will be such a thing which actually goes to infinity at that point. So when x double prime is not equal to x prime, it is 0. When double prime equal to x prime, it is not 1, but something whose integral over a short range would be 1. Okay, so that is what we learned in the last class. So let me clear this off. And if you expand an arbitrary ket, say alpha, a function phi alpha, psi alpha, whose ket representation is alpha in terms of the x prime, it will be alpha ket is equal to, since we are now no longer summing up, but we are into the integration. So it is integral of dx prime, and then we had expanded it. It is something we did in the last class, so I'm not explaining each bit of it. It is the projection operator. Normally it would be sum, but in the limit it is integral operating on alpha. So that is how alpha was expressed in terms of the x prime, that means in the position coordinate. What is this? What is the physical interpretation of this? Now this is actually I'll just get some space here. X prime alpha, if you take that and take the mod square of that and then dx prime, this actually is the probability that the particle will be found in a narrow region dx prime here around. So that is the physical interpretation of this fellow. Okay, and this fellow therefore is nothing but, so x prime alpha is nothing but the function represented by alpha. So I'll call it psi alpha at x prime. Okay, so this is what the probabilistic interpretation was, and this term that appears here is nothing but psi evaluated at x prime. Okay. Then we also did the inner product. Say beta alpha. This is evaluated as integral. And again, with d prime. Now again, we'll put in the x prime here. So it is beta x prime alpha. Okay, so see what we are doing. We are repeatedly just substituting this fellow, and if it is discrete, then we would have to sum it up. If it is continuous, we'll have to integrate it. But we are again and again putting this one in place of the identity operator. We are putting an identity operator here and just expanding it. And this we can easily identify as integral dx prime. Now here it is. Okay, what is this? Easily understandable, because that's what we did just here. We just did here. So it is basically psi alpha evaluated at x prime, and this one is its ulta. That means you can write this as x prime beta star. So it is nothing but the same thing with the star. So it is psi beta star. Okay. What does it physically mean? What it physically means is that, so this one, beta alpha, that represents the probability amplitude for the state alpha to be found in the state beta. Okay, so alpha, its projection on beta essentially physically means the probability amplitude for the state alpha to be found in state beta, and if this beta is a Eigen function, then we are essentially computing from here the probability of obtaining a particular eigenvalue related to that particular eigenfunction, the eigenvalue of the operator. Okay, so these are the things that we did earlier, and just I repeated it because what we'll do now is to go into the momentum space, and we'll see the same things actually apply in the momentum space. So we'll draw a line here, and we'll now go to momentum space. So far, we were doing everything in the position space. See, all these things were done in position space. Now, psi will be expressed in the momentum space exactly in the same way. We'll define the momentum eigenfunctions exactly in the same way as we did in case of the position eigenfunctions. So, so effectively, we are talking in terms of the p basis. So, in same way, we say that the operator p operating on an eigenfunction p prime will give the eigenvalue p prime times the eigenfunction p prime. Exactly the same thing that we did in case of this. And the inner product of p prime and p double prime will be the delta function of p prime minus p Okay, so delta function, I suppose you recall that when this p prime or whatever in the bracket is 0, it has a value. If it is non-zero, it has no value. But when you say it has a value, it's something that integrates to unity. And then the momentum eigengets, there's some space. Momentum eigengets have to span the whole space, huh? Ticket space. That means all functions can be expressed in terms of these momentum eigengets. Okay, and therefore an arbitrary alpha, arbitrary function alpha should be expressible in terms of these things, and exactly we'll do it the same way. We integrate dp prime, and then it will be what we did earlier for x, exactly the same way. We'll write this, and then operating on alpha. So what we did there, we are doing exactly the same thing in this case. Okay, and the meaning of this is again the same or similar. The physical meaning of this is that the probability that a measurement of p, here we are doing in p space, so we are measuring p of p momentum, gives the eigenvalue p prime within a narrow interval d p prime around the around the p prime. Okay, and therefore the p prime alpha. So alpha is projection on p prime. Its mod square d p prime is the probability. Okay, so this is the probability that a measurement of p gives eigenvalue p prime within a narrow interval dp prime around p prime is this. So that is the physical interpretation of this quantity. So far we are going exactly the same way as we went for the position basis. And then if the alpha vector is normalized, if it's normalized, then this quantity, I'll write here, integral dp prime alpha p prime alpha, this will be equal to, we know this, and therefore we can express it properly. We know this, and we know that this is its conjugate. So it is integral of p prime, and this is phi. Will signify that using phi, because we are now working in the p space. Phi alpha as a function of p prime, and its mod square, because the star and itself was there. This must be equal to 1. So that is the normalization in the p space. Okay. There's nothing very surprising about it. So far, there's no problem. I need some space. Let me clear off some space upstairs. And then we'll continue. Okay. Right. Now, when we took a discrete basis, then we knew that one basis can be converted into another basis. They can transform the basis from one to another, from A to B, we did. And when we did that, yeah, it was done using, for discrete basis, the transformation from A to B basis was given by an unitary operator U, whose the kth term, if you recall, we did that. Kth term is nothing but AKBL. This is what we did. So now, if you want to convert from X basis to P basis, we have to do something similar, right? But it is now a continuous basis. So for transformation, of X basis to P basis, so X basis to P basis, my handwriting. Yeah. For conversion of X basis to P basis, we have the same thing will have to be performed by here it was the old and here it is the new, and so we are converting from the X to the P. So this is what should perform the job. Okay. We are doing exactly the same thing that we did for the discrete basis, but now we are considering a continuous basis, X and P. And we are going from X basis to P basis. So we'll need to calculate this. What is this? In order to calculate this, let us first consider the X, we have to start with X, P operating on some vector alpha. Now, what is P operator? We know that the P operator, X prime, P operator is minus I H cross del X operating alpha. Now, what is it telling you to do? What it's telling you to do is to take a derivative of alpha, and then whatever you get, it's evaluated at X prime. Right? This is what the whole thing is doing. So if you have a function, it's you take a derivative at this point. Is to take a derivative and evaluate at a particular point. You get the derivative, or you take the particular point and take the derivative at this point are the same things, right? So effectively, this is the same as I'll bring this one out, minus I H cross del, sorry, this will be X prime. X prime of X prime. What we're saying is essentially that here it was asking me to first differentiate and evaluate at X prime. Now we are evaluating X prime and then taking the derivative. That's it. Should lead the same thing. So if this is so, then if I now put in place of alpha my momentum eigenvector P prime, then what do we get? Then X prime P operator operating on P prime, then it should give me this. So it is minus I H cross del x prime, and in case of alpha, I'll put x prime P prime. This is what we are trying to find out. Okay, so we are trying to find that out, and we are taking this route. Now, P prime operating on P operator operating P prime should give the eigenvalue times the P prime. So eigenvalue can be taken out. It will be P prime x prime. Okay, and this will remain the same, minus I H cross del x prime x prime. So I can see that it is now a differential equation in terms of x prime P prime. And so let us write it properly. It is derivative of is equal to it will be P prime here, P prime, this is minus, this will go downstairs, I H cross, and then x prime P prime. Okay, let me clean it up. It will be, because I said that I don't like I to be in the denominator, so it is I P prime by H prime x prime P prime. Okay, so it's a differential equation. You know the result will be an exponential function, so it will be x prime P prime. The solution will be of the form of a some constant times e to the power. It will be this I P prime, then x prime y h cross. Okay, and there will be some coefficient in front of that. Let's call it n, and we need to calculate what that n should be.
Excuse me, sir.
Yes.
So I'm not very clear about this, but suppose if you evaluate the wave function at a particular point, won't it become a constant, and then differentiating a constant will always yield a zero?
No. Here, what is happening is that there are two ways of looking at taking the derivative. Either you go here and take the derivative, or you take the derivative of the function. As a result, you get another function, and you get the value of the function at that particular point. Okay, so it is this what is happening. That means it is not getting a value and then taking a derivative. Point is that you are it has different values at different points. You are choosing a particular point, here, and saying that I'll now take a derivative at this point. That you can do.
Yes,
Or
sir.
you can take the derivative of the whole function, write it here.
I got it, sir.
Yeah.
Thank you, sir.
Let's go ahead then. So we have this n, and we need to evaluate what that n should be in order for this to be known. And this is the in order to transform from the x basis to p basis, this is what we need, and so we need to know n. So let's do that. We know that x prime and x double prime is something that you know, that it should be the delta function. But if you now expand it, it will be expanded in p basis. It will be p prime. It is x prime. We'll put I here and then expand in terms of p prime x double prime. Okay. Now this the left hand side we know it will be delta of x prime minus x double prime. And the right hand side, we know that this is here. So we can write integral dp prime, and this one is n e to the power, this one, I p prime x prime y h cross. What is this? It is the conjugate. It is a star of the same thing evaluated x double prime. So we'll write n star, and if n is a real number, then star makes no sense, but nevertheless, let me write it correctly. It is then minus its conjugate, minus I p prime x double prime y h cross. Okay, so this will be equal to, I'll take the mod n square up front, and then it will be integral dp prime, and then this one can be put together. It is e to the power I p prime, this is x prime minus x double prime by h cross. Okay. Now, is this quantity known to you? What this is? Actually, this follows from the definition of the Laplace transform. Let me just keep this one and work it out. So we need to evaluate this, right? So it comes from the definition of Fourier transform. So Fourier transform is f of k is 1 by root 2 pi. It is minus infinity to infinity, e to the power minus I kx fx dx. And the inverse transform is f x prime is equal to 1 by root 2 pi minus infinity to infinity. It is I k's now, e to the power I k, it was x prime, and this is f k dk. Now, if we substitute this here, get f x prime is equal to this two of this root 2 pi will become 1 by 2 pi. So it will be integral minus infinity to infinity. It is 1 by 2 pi. Again, it is, in place of this we are substituting, so it will be minus infinity to infinity. It will be k e to the power, now there will be subtraction on them, 2 e to the power, so it will be I k x prime minus x. If x remains, dx. Okay. Then we know that the integral of delta x minus x prime f x prime, this is something that we did in the last class, so we I'm just writing that. If you open the note of the last class, you will find this is actually fx. Okay, so this is what we wrote in the last class, and by reversing we can also write this leads to integral delta x prime minus x, because that's what we are trying to lead to, fx in place of x prime, we are writing s here. This is dx should be f evaluated x prime. Okay. So you now see that there is a, we can compare this with this, and that leads to the conclusion that 1 by 2 pi integral minus infinity to infinity, there was dk, e to the power minus I k x prime minus x, that should be equal to delta x prime minus x. Okay, we are just comparing this expression and this expression. We find that the whole thing, this guy, should be equal to this, and this is what what appears here. Where did I leave it? We left it. We left it here. Yeah. So that has to be now written properly. Just a minute. Yeah. Now I'll just erase this part so that we can continue here. We were in which step? Where are we? Oh, we were here. Yeah. From here we can erase, and we have concluded something about this. We'll just write it. So this is should be equal to uh, 2 pi h cross n square, and delta of x prime minus x. Okay, so this, what this thing is, we have now learned, and we have just substituted here, and as a result we can now evaluate what this is, because in the left hand side we have this, the right hand side we have that, and immediately we can see that n square should be 1 by 2 pi h cross, and if we there will be two solutions. If we take the positive real solution, then n equal to n equal to 1 by root. Okay, so we have found this, and if you substitute this, let me erase this part. If we substitute this, we find that what we what we set out to find out was essentially x prime p prime, and that has turned out to be that n, now we'll substitute 1 by root 2 pi h cross, and this is e to the power I p prime x prime y h cross. So that is the conversion formula we have directed. And if that is the conversion formula, then our alpha evaluated at x prime becomes integral of p prime x prime p prime alpha. This is something that we have just evaluated. So we can write this as, this is, we have already seen, this is psi function. Alpha is a particular function psi evaluated at x prime. That should be, I'll substitute this, so it will be 1 by root over 2 pi h cross integral p prime e to the power I p prime x prime by h cross, and then this is alpha evaluated at p prime. So that is the function in the momentum space. So function in the momentum space we are denoting as phi alpha, and it is evaluated at p prime. Okay, so this is what we have got, and this is first, and this. And now if you want to evaluate phi alpha as a function of p prime, that will become integral. Now it will be d x prime, and then p prime x prime, and then x prime alpha. Okay, and then if you now substitute that, you get 1 by plus, it will be integral of dx prime, and then it will be e to the power minus I e prime x prime by h cross. Now here it will be in the x basis psi alpha in x. Okay, so this is the, you notice that if you want to go from the x basis to the p basis, you have to take a Fourier transform, and if you want to go from the p basis to the x basis, you have to take the inverse Fourier transform. So this is the transformation of basis. Okay.
So could you scroll it a bit front? I mean, the previous part.
Yes, provided I have not deleted that, I can do that. Sorry. Why is it not going up? Yeah. Which part? Ask me to stop.
A little more, sir. Yes.
Yeah.
Yes, sir.
Yes. What is the question?
No, sir, I thought I missed something, so I'm just seeing if I understood it rightly.
No problem. All we did was, in order to find this, we found that this comes from a differential equation. We solved the differential equation, and there was a coefficient, and then we solved for the coefficient, found that the coefficient will be this. That's all we did.
Yes, sir. Yes, sir. Thank you, sir.
Great.
Oh, I have a question.
Yeah, sure.
Can you please again explain this bracket x dash and p dash? What is, I mean, what is it meaning?
We started by saying that in order to we earlier learned that in order to have a basis transformation of the A basis to B basis, these were discrete basis, we had to have a matrix whose elements were these. Okay, now we want to convert the X basis to P basis, so we need something here in the X basis, here in the P basis. Okay, so these are the Eigen Functions. These were the Eigen Functions in the A basis and B basis. Now we are talking about the Eigen Functions in X basis and P basis. So this is something that affects the transformation.
But in the fifth line, how did you write the 1 up p dash by I h cross?
Yeah.
Yeah.
Here? Yeah. So all we did was to take this one to the left hand side and this one to the right hand side. So p prime, this was already there. I have just divided by I cross. That's all.
Okay. And then exponential part.
I have just written it as a convenient differential equation form. That's all. Nothing more. और कुछ?
सर आपने ये assume करा है e to the power है पहले या फिर direct?
Again. I have assumed
you assume this e to the power I p dash x by h cross.
Yeah. Because the solution of a equation of this form, say dy dx is equal to something, say something ax, is exponential, right?
Yeah.
So that's what we have done. Sorry,
Okay.
ay. Sorry. So whatever this is, if you take that as a y, so effectively this will be the solution. This is something that we learned in the first year, right?
Yeah.
First order differential equation.
Yeah.
The solution will be of the form of exponential, and there will be a coefficient out front.
Okay. Okay,
That's
sir.
what we have done. Let me clean up the mess and let me continue. We will now need to sort out a few questions. The natural question is, how would the Schrodinger equation look in the momentum space? And you know that in the position coordinate, position basis, the momentum operator looks like minus I h cross del del x, and the position operator looks like multiplication of x, multiplication by x. So now we'll need to figure out what will happen in case of this. We go into the momentum basis. So okay, I just deleted it anyway. Let me write it again. So we said phi xt. Huh? Uh, no, I'll do it in the p basis. So I'll write pt. That means phi is a function, wave function expressed in the momentum basis. This we found that will be 1 by root 2 pi h cross integral minus infinity to infinity. It will be psi xt. This is in the x basis, e to the power minus I p x by h cross dx. Now, if you recall in the Schrodinger equation, in the left hand side it was I h cross del del t of the function. So we need to figure out what I h cross del del t of this is. So phi expressed in the p domain, what is this? This is what we are trying to find out. Okay. And in order to do that, let us operate with this in both sides of this equation. So in the both sides of this equation, the left hand side will be like that. In the right hand side, it will be, I'll bring this 1 by 2 pi h up front. And then it will be minus infinity to infinity. I h cross multiplied, so it will be I h cross and then del del t. Now we have to write this. It is psi xt e to the power minus I p x y h cross. Okay. Oh, we have started writing in the bottom. Anyway, we have to go to the top of some time. Anyway, now what is this? We know that this from the Schrodinger equation in the x domain. So we'll just substitute that. We know that this is 1 by root 2 pi h cross minus infinity to infinity Now this we know as for the momentum h square by first the kinetic energy operator twice m del 2 del x2 plus b of x whole thing uh, operating on psi xt. Okay, so this is equal to this, which we know from the known form of the Schrodinger equation in this basis. And then we have to write this e to the power minus I p x by h cross. Now we have got an equation that has essentially it's a summation. So there will be one term with this times this, there will be another term with this times this, right? And this will need to be, the first term will need to be integrated by parts because there are two things here. So here I have exhausted the space, so I'll go up, and we will now need to calculate what is this minus infinity to infinity. It is del 2 del x2 psi xt. See here it was, all this can be taken out. It's del 2 del x2 psi xt, and then this psi xt times e to the power minus I p x by h cross. This is what we need to calculate, px. We can do that by integration by parts. So it will be first this one e to the power minus I p x by h cross. Then this psi del x evaluated at minus infinity to infinity plus I p by h cross minus infinity to infinity del psi del x e to the power minus I p x by h cross dx. Okay. And now here del psi del x, psi is something that goes to 0 with slope also equal to 0 at the two ends, minus infinity to infinity. So this whole term will be actually 0. So only this term survives. And so we need to now integrate this. So we'll integrate this and check out what the results will be. So we need to calculate this. We are calculating this, if only this much. We are calculating this. So this is equal to then, this has to be integrated. This has to be integrated. This has gone to 0. Only this will be there. If you now integrate by parts again another distinct term will come out. So it will be I p by h cross square minus infinity to infinity. It will be psi x t e to the power minus I p x by h cross dx. Okay, so this has turned out to be this. Will there be another term? Yes, there will be another term. I'll write it here. Well, where or where B? We calculated this part, and we actually were trying to calculate this whole thing, which has two components. So one part we have calculated, the other part remains. Okay, so we'll now write the whole thing as I h cross del t of phi p t. This is what we tried to calculate. This will now become 1 by root 2 pi h cross p square by twice m integral this what we have got psi x t e to the power minus I p x by h cross dx. Then the next term, second term, is 1 by root 2 pi h cross minus infinity to infinity. It will be, there was a v term, v times this, yeah. V times psi x t. There was a this term here. E to the power minus I p x by h cross dx. All right. Now you see that this is nothing but the Fourier transform, including this, nothing but the Fourier transform of psi, and this is nothing but the Fourier transform of v psi, right? So we can now, in brief, write here p square by twice m, p square by twice m. The Fourier transform of this will be phi p t, and this one will be Fourier transform of p phi. This is again p and t. So you see, this is the Schrodinger equation. This is the Schrodinger equation in the momentum basis. This is the Schrodinger equation in the momentum basis. You see, that looks exactly the same. It looks exactly the same in the momentum basis. There is no difference. Okay. We are running out of time. We have to stop here. We'll continue in the next class. But have you understood that when you work in the p basis, we can convert the psi function into the phi function in the p basis and work out everything in the p basis, because the Schrodinger equation looks exactly the same in the p basis. And so this is effectively p square over twice m plus v is essentially the Hamiltonian operator operating on this. So this is where we stop today, and we'll continue the next week. Is there any quick question? No, probably we don't have time for the question today. If there's a quick question, we can answer. So the point is that whenever we have a situation where it is more convenient to work in the p domain, it's completely possible, instead of working in the x domain, we can work in the p basis. The only two things is that we needed an operator for x in the x basis, an operator for the p in the x basis. That's for something we already know. We need to find out what is the operator of x in the p basis, an operator for p in the p basis. That's what we'll work out in the next class. Let's stop today.
Hello, sir.
Yes, quickly.
Sir, yeah. So in the last part, sir, when you were finding out the coefficient of n, I mean the mod n squared, so you just compared the delta x dash minus x and delta x dash minus x double dash, is it?
I was trying to calculate the n.
Yeah.
Well, while doing so, we have deleted that. Anyway, if you go through the note, you will find that what we essentially worked out was, yes, the bracket of x and x prime calculated in two possible ways shows what the n should be. Okay, this is what we actually did.
Okay, sir. Okay. Yeah,
So
I got it. Yeah, got it.
n has to be that in order for the two sides to equalize.
Yes, yes, yes.
That's the point.
Yes. Thank you, sir.
Okay, let's stop. Huh?